Hello, welcome to Edexcel demola, and today's lesson we are doing enthalpy. Things are about to get very, very calculation dense, so I hope you got your calculators. Let's get into it. Okay, so we're going to kick things off by looking at enthalpy profile diagrams. But first, let's define enthalpy. Enthalpy is the total heat content of a system. Just lock that definition in. And something else that's really important is that equation there. So enthalpy, shown by this delta H, so that triangle is delta, is equal to the enthalpy of the products minus the enthalpy of the reactants. And your enthalpy change can either be positive or negative. We're going to get into that right now. So positive enthalpy changes are described as endothermic reactions. This means that the reaction is absorbing energy. So it's taking energy normally from its surroundings and is putting it into the chemical system, right? A key definition for this, and we're going to get more into it in the next video about bond enthalpy, but what we're saying is that more energy is absorbed when you're breaking bonds than what the energy released in bond making is. So when we're breaking bonds, we need to get energy in to break those bonds. When we're making bonds, we release energy. So we're saying there's more energy in that bond breaking process. Yeah. And as we know, if we're absorbing energy from the surroundings, then the surrounding is going to get colder. Right. So there are a couple key reactions that you should know that are endothermic: melting, photosynthesis, evaporation. Those are just a few. Now we're going to look at this enthalpy profile diagram. So the enthalpy profile diagram is kind of like just a representation of what's going on in the reaction, right? So you can see the reactants have less energy than the products, and that's because we've taken energy from the surrounding into the system, right? We're going to talk about these arrows a bit later, but you can see here we've got our enthalpy change there, so you can see it's going up, it's positive, endothermic. We've also got our EA, yeah, our EA stands for activation energy. We're going to define it in a couple moments. Now, if we had a negative enthalpy change, we're saying it's an exothermic reaction, right? Exothermic reactions release energy to the surroundings, yeah? So we have the converse of the definition we had for endothermic, yeah? More energy is going to be released in that bond making progress than is absorbed in that bond breaking process, yeah? Your surroundings are going to get hotter, yeah? So we're going to have combustion, freezing, respiration. I think freezing is kind of a weird one to be exothermic, but it is. So just know your surroundings are getting hotter: combustion, freezing, respiration. Yeah? Cool. And there's the energy profile here. So you can see this time, let's do a different color. This time the enthalpy is actually going down. So it's a negative enthalpy, right? And your activation energy a lot bigger. So let's actually talk about that activation energy. And also, just to point out, you got enthalpy on the y-axis and then the course of reaction or time on the x. Yeah? Just so you know for your enthalpy program profile diagrams. Okay, so activation energy, haven't talked about it too much here. It becomes a bit more important later when we get to rates of reaction, but it's the minimum amount of energy required for a reaction to occur. Just lock that definition in for now. It will become a bit more important later in the spec. Okay, so we're going to build layers to this, yeah? So now we need to talk about types of enthalpy changes. Now, before we get fully into that, let's quickly show this. So this like logo here, I've always thought of it like a TFL logo, yeah? If you live in London, you'll know. But the standard enthalpy change, yeah? So it's this enthalpy change under standard conditions. That's what it means. Now, standard conditions, just lock this in right now. Literally, remember it for the rest of your course. It's very, very important. So I'm going to say the pressure is 100 kilopascals, temperature is 298 Kelvin, or I'll just quickly add it on now, or 25 degrees Celsius. Just know you add 273 to convert. And the standard state is just its physical state under standard conditions. Yeah. So for example, water, 25 degrees Celsius, 100 kilopascals is a liquid. Cool. So enthalpy changes now. Enthalpy change of reaction now. This is a bit of a weird one in terms of compared to the rules for the rest. But enthalpy change of reaction is just the enthalpy change associated with a stated equation. So I've drawn that down, the decomposition of calcium carbonate, right? This one is not really relevant to the moles. You're just looking at the reaction. So if you had numbers in front of it, we also need to take that into account whenever you're doing enthalpy change of reaction. Cool. Not too much to talk about that, but now we've got a bit more of enthalpy change of formation. With these ones, I cannot stress it enough. You need to learn these definitions, yeah? You can get easy 1-2 markers just on the definition. So really important to learn them. So the enthalpy change of reaction, if I just zoom out a bit, is the enthalpy change when 1 mole of a compound is formed from its elements in their standard states. And you can see the example there with carbon monoxide. So the enthalpy change of formation for carbon monoxide is equal to carbon in a solid state. You have to remember your state symbols, plus half an oxygen molecule, yeah, goes to carbon monoxide. Now, why have we done half, right? Why would I not just, we'll do it in red because it's not right. Why would I not just say, okay, times everything by 2, make this 1, and that's 2. Now, because we're forming 1 mole of a compound. Yeah, we're forming 1 mole of a compound. That's really important. So making sure that your compound, your product at the end only has 1. Yeah, and that should only be 1 product ever. Okay. Something else you need to know, that the enthalpy change formation is going to be 0 if the element is in its standard state. So if I told you enthalpy change formation of oxygen, yeah, 0, because it's just an element in its standard state. Hope that makes sense. And yeah, just remember standard conditions. So it's going to be the state in under standard conditions. Yeah. Next one we need to talk about is enthalpy change of combustion. So again, zooming out, is the enthalpy change when 1 mole of a compound undergoes complete combustion. Yeah, complete combustion means we're forming carbon dioxide and water. We're not forming carbon monoxide at any point, or even just carbon soot. Yeah, you are forming carbon dioxide and water. Yeah, so I've got an example here with methane. Yeah, we're saying that methane plus oxygen goes to carbon dioxide and water. And again, we're mainly focusing on the 1 mole of the compound. So it's the 1 mole of methane. Everything else can have any numbers in front of it in terms of the stoichiometry. But we need to know that that compound that's undergoing combustion, that's reacting with oxygen, is only 1 mole. Yeah, that's the most important thing. Now, this one is always negative. I think we mentioned it earlier, that combustion is always an exothermic change. So if you get an answer that's positive for this, you've done something wrong, you need to check it again. And enthalpy of combustion is always negative. Cool. Last one that we need to talk about is enthalpy change of neutralisation. Now, this is when 1 mole of water forms from a neutralisation reaction. Yeah, enthalpy change when 1 mole of water forms from a neutralisation reaction. And simply, normally they're just really going to ask for the ionic equation. So I've just done it. H plus OH minus goes to H2O. And guys, this equation will come up time and time again in your A-level chemistry. Just make sure to get it locked in now. We also said neutralization was one of those reactions that's always exothermic. So just know that your answers should always be negative. Yeah. Okay, and now we are gonna get a bit more technical. Yeah, calorimetry. Now, something that you should know is that enthalpy change cannot be determined directly. Yeah, we need to go through different hoops and hurdles to get your enthalpy change. So one of these hoops is calorimetry, where normally it's going to be water. Give me something else sometimes, but normally water. We're gonna heat it up, yeah, and we're gonna measure the temperature change. So normally it will be a reaction happening. For example, I've got your apparatus up here. Normally it might be like the burning of a fuel or something. Yeah, that's going to release energy and that's going to heat up the water. Yeah, that's what we really want to do. And then we're going to use that to measure the enthalpy. So let's get on how to do that. The main formula is Q equals MC change in T. And correct me if I'm wrong, I believe that this is on your equation sheet. If it's not, I'll put something up on the screen, but I believe this is on your equation sheet. So Q equals MC change in T. We need to know what all of that means though. Q, energy change in, let's highlight things, in joules. Yeah, you've got to remember the units, very, very important, because that won't be on the equation sheet. Yeah, energy in joules, M, mass in grams. Specific heat capacity, this one I'm almost certain is given to you. That will be 4.18. That's the specific heat capacity of water specifically. Most of the questions will tell you to just assume that specific heat capacity is the same as water, or they'll literally just tell you what to use. Yeah, so don't stress too much about that. And then change in temperature. You can do this in degrees or Kelvin, just because we're doing a temperature change, it's literally going to be the same. Yeah, whether you're using degrees or Kelvin, so it doesn't matter too much. Now, the best way I thought to kind of learn how to do this calorimetry is just by doing a question. So, if you need to, feel free to listen to this part back if you need really to get more confident with doing the questions. Yeah. So, I've got an example there. I've cut out a lot of the questions, so just know we were working with combustion of butane. Yeah, we're calculating the enthalpy change of combustion of butane. Yeah, and you got a table there. You will a lot of the times have this table, so it's really important to know how to use it properly. So, step 1, we need to calculate the moles of butane. Now, because we've already done videos on this, I am gonna not really say all the formulas that we need to know. I'm not gonna write them out, but we should know these formulas. Yeah. So first of all, to calculate the mass of butane, I need to know to calculate the moles of butane, I need to know what the mass is. Yeah. I know that the lighter contained butane. Yeah. As combustion was occurring, butane is getting burnt off. So the difference between the mass here and the mass here is going to tell me the mass of butane that got burnt off. Yeah. So that's what we're going to do first step. We're going to do 14.86 minus 14.39. You get 0.47 grams of butane. Cool. Then I need to get the molar mass of butane so I can get the number of moles. Yeah? Molar mass of butane is 58. So we do the 0.47 divided by 58. We get 0.008103 moles of butane to 4 significant figures. Yeah? Okay. We've left it at that. We found the moles of butane. Let's go. We need to get the temperature change. Yeah. So that we can use that formula Q equals MC change in T. We need to get the temperature change. So let's look at here. We said that before heating was 19, after it was 74. So just know the temperature. Let's make a note there. Temperature has gone up. Yeah, that's going to be important later. So we'll calculate that temperature change, 55 degrees Celsius. Happy days. Now we can just plug it into the formula. Yeah. So mass. We're measuring the mass of the thing that got heated up. That's what you need to know. So like sometimes you'll put two solutions together. You'd have to add those solutions together, right? But in this case, we're heating up the water. We're not heating up a solution. So I can just use the mass of water. So we're going to look at the table. Mass of water is 50 grams. Yeah? Okay. So 50 times specific heat capacity times change in temperature gets you 11495 joules. And we're going to divide it by 1,000 just so we're in kilojoules. That's what we want to work with. So 11.495 kilojoules. Now, to get the enthalpy change, and guys, I can't stress this enough, check the sign. It's an extra mark if you get the sign right, but honestly, it's a mark you don't want to lose. So we're going to do energy divided by moles. Energy divided by moles is going to give you the enthalpy change. So we're going to do that, and what you should get is 1,419. Yeah, I've rounded it up to no decimal places. Yeah, okay. One last thing to do. I said check the sign. If the temperature went up, it's an exothermic reaction. Plain and simple. If the temperature's gone up, it's exothermic. Meaning, we need to add a negative sign here. And then again, I'm going to tell you something that as well. Because we were working enthalpy change combustion, if it wasn't negative, I know I'm wrong. Yeah? So, negative symbol there. Okay, I promise you we're almost there. We just need to look at the limitations of calorimetry. So, this is just like, it does come up sometimes in exams. It's not like the most important thing ever, but I think it's just nice to know. So with limitations of calorimetry, normally it's going to be about heat loss to surroundings or combustion didn't complete. Yeah, those are the main two that you're going to see. There's probably more. I would say if you come across this in a question and it's not one of these two, which I'd be really shocked, you can just look at the mark scheme and then copy down some more reasons. But these are the main two. Yeah, and both of them are going to cause a less exothermic enthalpy change than the true value. And that's because that means that the energy change we calculate is going to be lower, right? Cool. So we know those limitations. How do we kind of mitigate them? Well, you can put a lid on, yeah? If you put a lid on, that's going to mean less heat is going to surroundings. You can use an insulated cup, which is also going to mean less heat is being lost to surroundings, yeah? A bomb calorimeter can also be used. I didn't say that, but a bomb calorimeter can be used, yeah? And I've got one down here. So this is a bomb calorimeter. Again, I wouldn't really stress about like learning different parts of this. Like, just know that's a bomb calorimeter. Yeah, literally. Just be able to, if they show you that in the exam, just be able to say it. And then one that's always good for improving accuracy is just repeating and calculating a mean. So those are just some good reasons to know. Okay, nice deep breath. We've got two questions for you to try here. So see that first question. I'd just implore you to like pause here and then pause again when I show the next question. We've got two parts to this one. So standard conditions and then the enthalpy change of formation. And then here, we're doing the calorimetry. So yeah, I have a go at those. Okay, so hope that was all fine. Let's look at the answers. So first one was standard conditions. And honestly, I think that this question is kind of like, I thought this question was really easy, right? Yeah, so just be able to list it off. 298 Kelvin, 100 kilopascals. What I really thought was a shame is that only just over half of people are getting this right. Like, I don't want to be too harsh, but this is basics. This is very, very easy question. So make sure that you're not the people losing marks on this because this is an easy mark to gain. Yeah? Now, enthalpy change of reaction. So I told you at the start of this lesson that enthalpy change of reaction is enthalpy of the products minus the reactants. So we need to calculate that. Yeah? And enthalpy change of reaction, we also have to look at the stoichiometry, right? These are things that we said. So I'm looking at the products, yeah? We've got 4 nitric oxide, or 4 NO, and we've got 6 H2O. And on the other side, we've got 4 ammonia and 5 oxygen now. First things first, I'm looking at the oxygen, I'm saying that is an element in a standard state. So this is going to immediately have a 0, yeah? Cool. Just so you know, because we were using formation data as well, yeah? So that's going to have a 0. Cool. Let's have a go now. So I'm saying products. So we had the 4 of the NO, yeah? And we had the 6 of the water. and we're taking that away from the 4 of the ammonia, and then we said 5 times 0 because it's just oxygen. Yeah, and that's going to equal to our enthalpy change of reaction. So we put everything in the equation now, and then literally we're following it like we would in maths. Yeah, I've done my calculations there. You can pause and read through it. The answer that you should get is positive 90 at the end. Hope that makes sense. But yeah, just look at those mathematics. That should make sense. If it doesn't, drop a comment below. I'll be happy to answer. Then for this one, I thought the mark scheme actually drew this out much nicer. I didn't like what the mark scheme was how the mark scheme was explaining it the last one. But literally, this one again, we're following our steps. So that's them using Q equals MC changing T, right? Just look at what they've given you here. So you can calculate this. This is the change in temperature. That is about 28 degrees Celsius. Yeah. And then what we're also saying is that this is the volume that you're using. So that's the volume of the silver nitrate, which is what you're heating up. Yeah. That's fine. And then they've probably said, yeah, assume that the density and the specific heat capacity is the same as water. So we can use the 4.18. Yep. That was the first step. Then moles of the silver nitrate. Yeah. Moles is equal to concentration times volume. Yeah, fine. All they had to do is to convert to decimeter cubed. But other than that, shouldn't be too much problems with that. Yeah, and then you got your moles. Okay. Next step, we can find the enthalpy change per mole, right? So just remember, what you would have seen in the question is it said, let me find it here, all the aqueous silver nitrate reacted. In my head, that means it's the limiting reagent. Yeah, if that's the limiting reagent, that means that we need to do this times 2. Yeah, we need to do this times 2 to get the enthalpy change of reaction. That's what I've just locked into my head. So looking here, we found the enthalpy change. Yeah, we found the energy released. Yeah, so when we have that, and just so you know, again, we've done energy divided by moles. You found the change, and then you just need to times it by 2. Yeah, and remember why we times it by 2? Because 2 moles here. I'm happy to elaborate in the comments because I feel like that was a bit of a mean question to start off with. So any questions again, ask in the comments. It is a difficult concept to wrap your head around. Okay, I've done a lot of talking, so I'm happy to wrap this up with the A-star tips. Now, things that are good to do for enthalpy, yeah? Learning the equations, yeah? Honestly, even the Q equals MC changing T, I would just commit it to memory because even if it isn't a data booklet, yeah, it's just easy if you just know it off by hand, yeah. And then all of those equations to do with like moles equals concentration times volume, you are gonna need those. You never stop needing those, so make sure they're learned. MVP profile diagrams again, I think it's a good one to learn because at the end of the day, there's not too much complexities to it. Yeah, there's a lot harder things in this A-level chemistry course, so that's good to learn. Difference between exothermic and endothermic, also good to know. So example definitions, really cannot hammer enough. Definitions are so important in chemistry. They are easier marks to pick up compared to like your conceptual stuff. So make sure that you're getting those marks. And then also the calorimetry questions. I know there's only 2 examples in this video. I'd implore you to keep on going at them. Just keep on going at them. Know what kind of nuances are going to come up. And then I'm sure that you'll be able to do it well. But yeah, just keep on practicing those. And then what do we not want to do? The definitions for exothermic and endothermic can get confused because, like all of science, they love using similar words. So just make sure that you know completely difference between exothermic and endothermic. Standard conditions. I couldn't believe I was reading the examiner and more than 50, and they said just over 50% of people got that. Guys, we need to be better than that, okay? So remember your standard conditions, 298 Kelvin, 100 kilopascals, yeah? Enthalpy changes, most of them are looking at 1 mole. So just remember that most of them are looking at 1 mole. That's why we had that little change when we did the question that I gave you there. Just make sure that you know the exception is the enthalpy change of reaction. So that's what we had to times by 2 as well. Cool. And then calorimetry, limitations, fixes, just know them. I feel like a lot of people don't. So if you do, it can set you a bit apart in the exams. So I hope that video was helpful. I fear it might be a bit long, but you know what? At least the content's been covered. Any questions at all, drop them in the comments below. I'll do my best to answer. If you found the video useful, please like, subscribe to the channel. We've also got the TikTok and the Instagram, both at A-star demola. New content's coming up on those, and I'll catch you guys in the next one. Bye for now.